So I think we can look on the sewage systems of cities as reformable. As Sydney is going beyond reform, it looks like it's going to drive caves under the sea and let its sewage go way out to sea, so it's going to have trouble getting out there to get it back again. But small settlements are not beyond reform. And dryland settlements throughout Australia can be producing most of their biomass energy out of their sewage. Plus, if you like, a lot of their food, if they are so inclined. So what we're looking at now is water from its origin, doing its duties, where we polluted, making the pollution part of the regenerative technology. And now I suppose at last we're faced with the question of cleaning up pollution in water. Getting out the heavy metals, getting out the radioactives, getting out the acid and getting out the modern chemicals. Well, where there's life, folks, there's hope. So we're going to do it for you. This is all nice up-to-date stuff too. Here comes the water. Pollution in. It contains acid, a whole set of heavy metals, double plus iron metals that is, a whole lot of chlorinated hydrocarbons, or even brome substances, bromic substances, chlorine or bromine. What else we got? Radioactives. The usual soup, the standard city soup coming in. It's been through 9 sets of kidneys and it's coming into your system. Now what are you going to do with this? Well, the first sensible thing to do is to drop your pipe down a pit and fill your pit up with oyster shells. So now on she goes, right. She now overflows your pit and away she goes. Now what we did there was, and it's easy to observe, we did 2 things actually. On the oyster shells grow a lot of algae, and the oyster shells give up their calcium to neutralise the water. As soon as we reduced the acidity, we reduced the capacity of the water to carry those heavy metals, and a lot of them now fall out as insoluble gunk, which we've got to take out through a sump. And we've got to feed in oyster shells according to demand. But it's quite, for a small settlement system, there's not much demand. You keep a few bags of shells there.
Can the lime chips have the same effect?
Lime chips quite good. Just I put the whole thing in a biological mode here. Actually, I'd much prefer here to use freshwater mussel shells, right? Now, the other thing in our water, of course, is E. coli and very dangerous compounds of nitrogen. We'll call them azotes, nitrites and nitrates, kidney blasters. Things that make your kidneys rot out and drop off. And some salt. You can chuck a bit of salt in too. We got all those in there. We got all those in there. That's your agricultural and that's your industrial waste. These are nitrogenous compounds.
But oil and stuff like that. Right?
Yeah, that's in there in your hydrocarbons. It's chlorides, fluorides and bromides are linked up with the hydrocarbons in terrible association. 2,4-D, 2,4,5-D, dioxin, PCB and P-double-B. They're all in there, flowing downstream. Okay, now out of the oyster pit it comes. Now we can put at any point before or after the oyster pit. It may actually. We can also be able to put silt in our water, I guess. We can actually put it through a sand filter. Now that sand filter is like that, right? But it's built in two parts like that. And the intake comes in here. We'll take it through a sand filter now. This is quite fine, coarser sand, gravels, and then the same thing again, and on it goes, right? Now this sand pit has another pipe into it, down the bottom, and that is opened about every 6 weeks and pushes the water back up the sand pit. That's the flush pipe. It cleans the filter. Just as this one has a sludge pipe out of it, so that one has a pipe going in to flush out the sand filter. So after that you have no turbidity. That takes out all particles. Then it goes, say, through your oyster pit. So this is 1, 2. Now on it goes, right. Now here's a little sill, and it goes now into a broad channel. And the channel has in it, in different successions, the first thing we get into it is a scirpus, which is a rush, called a club rush. Okay? If it's in Europe, we put Scirpus validus, but we've got a lot of Scirpus, and they're the triangular rushes. So now fairly neutral, silt-free water, still carrying hydrocarbons and heavy metals, enters the Scirpus. And it still carries some E. coli, although a lot of that also now has gone. It died in the sand filter. However, we dealt with this part of the problem, and in dealing with any part of it, we also dealt with part of that problem. And we dealt with the silt problem. And we dealt partly with the E. coli problem. Part of the E. coli has been eaten by the algae on here, and part has been eaten by bacteria which eat E. coli in the sand filter. Now, but we've still got the PCBs and the radioactives. Now they go into the Scirpus validus trough. That's growing on a mat or a floor of topsoil. And that does a whole set of really extraordinary things. It continues it alters the pH back to about 7.5. It'll adjust it from some ranges between 9 and 3 down to about 7, and it will either exhale nitrogen or not. Scirpus validus is pretty good at pH adjustment. And it can give off nitrogen. It may very well be that it becomes an efficient hydrogen-producing system for us, but we haven't gone that far.
You can use any species of that genus.
Scirpus generally is good at this. Scirpus validus, Scirpus, there's several of them, 4 or 5 species. It grows everywhere, from the sand dunes to the swamps. It's a little swamp rush, club rush. We've got them in every state in Australia and every country in the world. It's a little triangular guy. We'll get on to another one in a minute. We'll go to Juncus in a minute. Juncus is that round guy where it has the thing and then a spike, you know. And Scirpus isn't. Its fruit is at the top of the rush. Small fruit, about 1/4 inch brown fruit. Juncus is that dead round shiny one with a pithy middle. Now Scirpus has a remarkable property of breaking down chlorinated hydrocarbons, providing you don't overdose it. It breaks them down and incorporates them into the plant material as harmless compounds. It also holds the residual heavy metals in the plant, and it can function away on quite high proportion of heavy metals. So it does the rest of the acid, heavy metal and chlorinated hydrocarbon bit, and it also puts paid to a lot of the radioactives. Mind you, some of the algae in here and in here selectively hold out radioactives. They become radioactive, but at least I've got them locked up. Scopus can be cut, and the normal arrangement that you do is a trough and bank system with your cutter bar going along here, your scopus growing here. I can cut the scopus, and you can use the scopus as a biological fuel in two ways. You can either compost it and get heat out of it, or you can fire it. When you fire it, you get your heavy metals back out of the ash. So it's best put to destructive distillation. And from when you fire it, you get a lot of methane off as a byproduct, methanol, furfural, all those byproducts when you burn it. And you get methanol. For every tonne of it, you get 6 gallons of methanol, 4,000 cubic feet of methane, and so on. Basically, you cook it inside a drum by burning some of it to cook the rest of it. The residual ash has your heavy metals in. The chlorinated hydrocarbons were broken down by the plant itself. They're not there. Radioactives also will remain in the ash. They can be reburied or do what you like with it. You can put it through electrolysis, reconcentrate your uranium and throw it at Charles Court or somebody.
So there's no real getting rid of it, is there?
Yes, of course there is. There's no getting rid of it to start with, was there? It's down in the ground. You can drop it down a hole down a uranium mine. You can put it on a trolley and run it down a uranium mine, tip it out. Okay. You go on into Juncus, which has a great affinity for these E. coli and for the... It does something terrible to the E. coli. It sucks them up and gets rid of them. And also, it takes up a lot of the the nitrogen compounds. Now, the water is looking pretty good, except it's liable to contain too much phosphate from soaps and also from animal remains. And finally, you put it through a bed of freshwater mussels, and they're the world's best phosphate fixers. They are the highest reservoir of phosphate in the total ecosystem. What they do is some of them work at 200 gallons a day per mussel, sucking it in, taking out the phosphate and pumping it out of an anal tube into the mud, and then it becomes fixed into the mud where the mussels are. There's no trace of E. coli left. You can now test your water and find that the E. coli count is lower than if you had chlorinated the water. But unlike chlorine, it doesn't give you cancer. In the mud under the mussels. Yeah, so periodically you sieve your mussels, throw your whole deal up onto a sieve, wash it down, put your mussels aside and pump the whole lot out onto your paddock. That's right, that's what you do with it.
The mussels have been known to reproduce in evolution.
Yes, they reproduce. Don't forget your mussel shells go back to the start of the system and start... Pardon? Well, I wouldn't eat them, because what you're asking them to do is to take out some phosphates and maybe the residual E. coli.
Who worked that system out?
This one, the Max Planck Institute in Switzerland. They did all that work on the Scarpus and Juncus and that, and they published it. It's excellent work. And then this one, that's Bill Mollison. This one is old as old. That sand filter is one of the oldest systems of reducing pollution that we know about. It's been used from pre-antiquity. The next one, well, it's kind of Bill Mollison, but it's kind of pretty old too, liming water.
And
So,
anybody actually put this together?
no, I don't know of one that exists. I don't know of one that exists.
So the way you do the water, you're going to drink it or?
Yeah, you can drink it now. It's pure, sparkling, pollution-free water. You can dip your glass in the other end of that system and drink it. There may be one. I first designed it for a place at Benalla about 9 years ago, and that's when they were forced to pump by windmill from a paddock which had a lot of cow and sheep manure on it. And we designed this system. They were going to do it with a 3/4-inch pipe run through. Whether they did it, I don't know. But I still got the report in which I designed it. Too often I never go back. No, you want a bigger place for a bigger scale. There are actually, I'm wrong to say they're not actually operating. There are some of the Scarpus and Juncus systems are operating in Switzerland and Holland on reasonable scales, right? And what they consist of in ground plan is a series of sealed troughs. These are actually little pipes, right? And they tractor through here, cutting off the rushes. And they actually use quite a lot of them in basketry. So you take off, make baskets, yeah. No, not necessarily. And we've also got a testing running. I don't know whether that's finished. We sent water from a system which is naturally full of Juncus. We found a place. There's a place called the Truckee River, which carries the raw sewage of all the gamblers of Reno, plus a lot of other industrial pollutants. There's a diversion canal going through the Indian reservation, and first enters a huge Juncus system, and then off that it irrigates fields, and then it falls back into the Truckee. So recently we gathered water from there and here, and we're going to see what that Juncus system did, because we are absolutely persuaded. It looked good at the other end, smelled good. Up here it's practically dilute sewage. Yeah. It's some material. What it is, it's insoluble calcium compounds of heavy metals. Well, you do what you like with it. You can put it in an electrolysis bath and get your heavy metals back as pure metal. A slug of cadmium or a slug of zinc or whatever it is. Make a gold ring out of gold, silver brooch out of silver. Put your zinc to work in galvanising and put it back to use. Throw your cadmium away. Now that does it. Those systems are now very well documented. And there's not much left coming out of that. Point out to you that everything in that is alive or was alive. It's all a living treatment of water. Only life systems seem to be. This is a surprise that these plants are breaking down the chlorinated, the PCBs and dioxins, and they are doing it. And actually the metabolic processes are half known. How they're doing it is half worked out. It's not totally worked out. They're giving off gases which are part of the system. Unless you actually rush a lot of stuff through, a lot of 2,4-D through, the things will stand up very well. If you've got half drinkable water, they'll work indefinitely.
Bill, you were saying it's been fairly well documented. What's the where?
From the Max Planck Institute, in Zurich, I think. Most of the work is being done and is going on there. It's current. It was only last week that I got some of the hard data from Berlin.
Who financed
I'm not sure. Is it something to do with Steiner schools? Who's Steiner person?
Yes, I think so.
I think some of the people there at least work with Steiner systems.
Most of the work on the flow problems has been done in the Institute of Norway, where they run a really big way.
This is a section of the Max Planck Institute. It's called the Biological Water Treatment Section. It's got a terrible German job.
The other curious thing, a lot of the work's being done by architects. It doesn't normally think of delving into this sort of business.
These people are biochemists by training.
The flow problem work.
Oh yes, that was sculptors actually.
That makes like
Yeah. CKE.